So far, so far we looked at distributions having only one parameter, like for example, exponential has only one parameter, uniform zero theta only has one parameter, and so on. But right, but many of the non-distributions have two parameters or more. So for example, if you look at examples, guys, like for example, the normal distribution, the normal has two parameters. Okay, and the log normal distribution also has two parameters, right? The beta distribution, which we did not talk about, you may talk, I mean, I think it's in the handout I gave you. It also has two parameters. The gamma distribution, which is also in the handout I gave you, has two parameters. So the question is how to do the MLE, the maximum, the estimation of the parameters by MLE when you have more than one parameter. So in this hour, I would just talk about the two parameter case, although it can be extended to multi-parameter case too. So I'm going to talk about I'm going to show you what to do two parameter MLEs. So first of all, I will start by giving the procedure for finding the two parameter MLE. I mean, earlier today, I reminded you how to find the MLE for one parameter MLE. Okay, but now you have, okay, suppose now I'm considering the case where you have two parameters. Suppose you have a data set, say random sample x1 to xn, IID with probability density function f, say with two parameters, say theta 1 and theta 2. So for example, theta 1 could be the mean parameter for normal, and theta 2 could be the standard deviation parameter for normal, right? And we want to find the MLE of theta 1 and the MLE of theta 2. The question is how to do that, all right? The first step, A, is to write down the likelihood function. In this case, the likelihood will be a function of theta 1 and theta 2. right? Because you have two parameters, and it will be the product 1 to n of right. So this is the product of the density function over the n data points. Right, that's part A. Part B of the procedure is to take the log of the likelihood function, which will be the sum of the logs, right? So it will be okay, this is the log. And part C is to, because you have two parameters, you need to do the partial derivatives, not ordinary or not ordinary derivatives, but partial. I'm sure you guys know partial differentiation, right? So you need to do the partial differentiation with respect to theta 1 and with respect to theta 2 and set them to both 0, right? Okay. Now, okay, okay, let me call this 1, call this 2. Okay. Okay, so we need to solve these two equations, 1 and 2, right? So let the solutions be theta 1 hat and theta 2 hat, right? So that's part C. Now, finally, part D is this. If the following is true, if the if the second order derivative of the log likelihood with respect to theta 1, I mean the partial derivative at theta 1 equal to theta 1 hat is less than 0, and we need an additional condition, right? We need an additional condition which is as follows. Okay, so if these two conditions are satisfied, that is the second order partial derivatives of the log likelihood with respect to theta 1 is negative, and this term here is positive, right? Then is Emily of this. So do you see that it's more complicated than in the one parameter case. So it involves more calculations. So So the first, just to go through it again. So the first step is to write down the likelihood function. The second is to take the log likelihood. The third is to take the partial derivative and set them to 0. So you get two different equations. And you need to solve the equations for theta 1 and theta 2, and let theta 1 hat, theta 2 hat be the solutions. And the fourth step is to check if these two conditions are satisfied. If they are, then the solutions that you got in step number 3 is an MLE of theta 1 and theta 2. So this is the procedure you'll need to follow to find the. I mean, you will learn this in semester 2 next year when you take the course statistical methods, which I will not be teaching anymore. I'm not. I mean, I don't teach any of the year 2 courses, as you know. I only teach year 1 and year 3 courses. So I'll miss you guys. But anyway, I just wanted to give you this so that you know this before you go to semester 2 of year 2. So let me start doing some examples, starting with the simple example, which is example 1. Okay, suppose and this is the most popular example where you have a data from a normal distribution with two parameters. The first parameter is mu, the population mean. The second parameter is sigma squared, the population variance. So we want to find the MLAs of mu and sigma squared. Okay. So we need to follow the procedure that I just described to you. So the first step, A, is to write down the likelihood function of mu and sigma squared, which is gonna be the product of the density function. I'm sure all of you know the density of a normal distribution, which is this, right? All right, this is the density of the normal distribution. Now we need to simplify this, which is not hard. Okay. So this is the simplified form of the log likelihood. So the likelihood, right? And the next step is to take the log of the likelihood function. So that's what I'm going to do now. So if you take the log of the likelihood, you get minus okay, and minus Okay, guys. So that's step number 2 for parts, and step number 3, part C, is to find the partial derivatives of the log likelihood with respect to the two parameters. So let's find the partial derivative with respect to mu first, right? So with respect to mu, you will get this is the partial derivatives, right? And of course, this can be simplified further. The 2 and the 2 will cancel, the minus and the minus will cancel. So this will be 1 over sigma squared times the sum of this, right? And this is, now if you take the sum inside, guys, you can write this as the sum of xi minus the sum of mu. Okay, you like this. Okay, and this will become 1 over sigma squared times, excuse me, sum of xi. The sum of mu is simply n mu, right? Okay, so let's put this equal to 0. Let's call this equation 1. Okay. Now we also need to differentiate do the partial derivative with respect to the second parameter, sigma squared or sigma. It doesn't matter which one you use. So if you differentiate with respect to sigma, for instance, you get n over sigma plus 1 over sigma cube times you set this to 0, and let's call this equation 2, right? So you have two equations and you have two unknowns. The unknowns are mu and sigma, or sigma squared, right? So we need to solve these two equations for the two unknowns. Right? So from equation 1, you can see the solution for mu, let's call it mu hat, right, is this, right? This is the solution for mu hat, which is clearly the sample mean, x bar. All right, and excuse me. And from equation, that's from equation 1, sorry. From equation 2, you can see that the solution for sigma squared hat, all right, is equal to 1 over n right, squared. Now I'm going to replace mu by mu hat, right? So this will be 1 over n times the sum of xi. Mu hat we already know is x bar. Is this. All right, so the solutions of the two equations are, the solution for mu is x bar, and the solution for sigma squared is 1 over n times the sum of the deviations. So sorry, sum of the squares of the deviations, right? So that's, we are done with part C. Now the last part is we need to check the two conditions which I mentioned earlier. right? Now to check the conditions, we need to first find the partial derivatives, right? So let's see how we can do it. The first thing is you need to find the partial derivative with respect to mu. What do you think? We know the partial derivative with respect to mu is this one here. This is the partial derivative. Now the second order partial derivative of this one will be what? It will be, I mean, if you work it out, it's not difficult. It'll be, I'm not gonna, well, I mean, I'm sure you guys know better than me how to differentiate things. You did one full semester of calculus. So the second order partial derivative with respect to mu is gonna be n divided by sigma squared. Okay, you can see that, right? I hope so. And the second order partial derivative with respect to sigma, right, is gonna be n over sigma squared, I think, minus 3 over sigma to the power 4 times the sum of xi minus x bar. Sorry, not x bar yet. I mean, I need to keep the mu, not replace it yet. So minus mu. Okay. All right. So that's the second order partial derivative with respect to sigma. Now the mixed derivative. Remember, the mixed derivative is with respect to mu and sigma, right? So it's gonna be minus 2 over sigma cube. Correct me if I'm wrong, but it's quite possible. I mean, if I'm wrong, please let me know. Times the sum of xi minus n times me. So these are the three partial derivatives that we need. Now, before we go further, right, before we check the two conditions, right, we need to work out these partial derivatives at the estimate for mu and the estimate for sigma. So it follows from this that so the value of this at mu equal to mu hat, right, is equal to simply the same thing, right, because it's not going to change. There's no mu hat in this expression, all right, and the value of the second one, with the second derivative, partial derivative, gonna be equal to n divided by sigma squared at minus 3 at, then you have the sum you have this, all right? So we are working out at, you follow what I'm saying. Well, I mean, if you have any questions, please use the chat box, right, or use the microphone if you have one. Okay, so I'm just replacing the sigmas and the mu's by hats, right? And we know what the hats are from the previous part C, right? We know from so if you substitute for sigma squared hat and sigma to the power 4 hat into before we do the substitution, let me do something. Let me pull out one hour. Okay, I'm gonna replace mu hat by x bar, which is the estimate that we got in part C, right? Okay, now if you replace sigma squared hat by the estimate that we got in part C, what you will get is the following. You will get n minus 3n. This is what you will get, because remember in part C we got, if I can go back to part C just a minute. Okay, it's this one. In part C we got the estimate for sigma squared as equal to this one, right? This. Now if you replace this by this in this expression, right? In this expression, if you do that, then this thing here reduces to minus 3n, right? So this is equal to simply minus 2n divided by this. Okay, so that's the, okay. Now finally the mixed derivative, which is this one, the mixed derivative at mu equal to mu hat and sigma equal to sigma hat, it's gonna be minus 2 divided by sigma cube hat times the sum of xi minus n mu hat. Okay, now we know that mu hat is the sample mean, so let me replace it already. So I will replace mu hat by x bar. Okay. Now clearly the sum of xi minus n x bar is 0, so this is clearly equal to 0, right? Okay. So what we have done so far is to work out each of the 3 partial derivatives. I mean the second order, they are all second order partial derivatives at the estimates that we got in part C. Okay, now we can check the 2 conditions. We need to, okay, the first condition, remember, is the condition that the first condition must be that the second order partial derivative of the log likelihood with respect to mu at mu equal to mu hat must be negative. But what we have is n over sigma squared, which is clearly negative. So this condition is clearly satisfied. Okay. Okay. And the second condition is that is the following, that that's this thing here at mu equal to mu hat minus comma sigma equal to sigma hat, right, must be positive. Right, let's see what it is now. Okay, the first term is clearly equal to minus n over sigma squared, right? And the second term is minus 2n over sigma squared. Okay, and the third term is 0. We just showed it is 0, right? So clearly what you have is is 2n squared divided by sigma power 4. And this is clearly positive. So both conditions. So the two conditions, there are two conditions that needed to be satisfied. So both conditions are clearly satisfied. So hence the conclusion is that hence the x bar comma 1 over n times what are MLEs. Do you guys follow this? I mean, it looks like a long process, but I mean, once you do a few examples, you will get used to it. I mean, okay, so okay, so do you have any questions on this example that I just did? Okay. Okay, so do you have any questions on this example that I just? Okay, any questions on this example, guys? Please let me know. Hello, guys. Are you okay? Any questions so far on the example that I just did? So this is a typical example. Okay, thank you, guys. All right, this is a typical example that you will encounter in year 2, semester 2, when you take the course statistical methods, right? Okay. All right, so now let me show you just one more example. If I have time, I will try to do it. Example 2. Okay, so you have, this is the ln obviously stands for log normal distribution, right? Okay, so this is similar to the first example I did. So the first part is to write down the likelihood function, okay, which will be the product Remember, the density of the log normal distribution is something like this. If you don't know this, I'm sure I gave this in the handout on the first day of classes, so you may remember this. I don't know. All right, this is the density of the log normal. So you just take the product of it from 1 to n. Yeah, this is the simplified form of the likelihood function. All right. So that's part A, and part B is to take the log of the likelihood. So you get minus n over 2 times log of 2 pi minus n log of sigma, right? Minus, excuse me, sorry, what happened? Minus the sum 1 to n of log of xi, right? And then minus 1 over 2 sigma squared. So this is the log of the likelihood, part B. Part C is to take the partial derivatives with respect to the two parameters. So the first, with respect to mu, you get minus 2 sigma squared times 2 times log of xi minus mu times minus 1. Okay, this is similar to the previous example. So if you simplify this, as we did in the previous example, this is what you get. You get in brackets the sum of log of xi minus n mu. Okay. All right, and let's set this to 0, and let's call this equation 1. Okay. Okay, and then now we need to do the partial derivative with respect to sigma, right? So that's gonna be n over sigma plus 1 over sigma cubed equal to 0. So let's call this equation 2, right? So you have two equations and two unknowns. Now it's clear from equation 1, the estimate for mu is equal to 1 over n times the sum of log of xi. Okay, you can see that clearly, right? And from equation 2, you can see that the estimator for sigma squared is 1 over n times log of xi minus mu hat squared. Right, so these are the two estimates for mu and sigma squared respectively. All right. Okay, guys, are you with me so far? Okay. All right. The last step is to show that the part D. Okay, we need to show that the two conditions are satisfied. Right. So the first thing is that you must find the partial derivatives, second order partial derivatives. Okay, this is the second order partial derivative with respect to sigma, and with respect to with respect to mu. With respect to sigma, you will get n over sigma squared minus 3 over sigma to the power 4 times this. Okay, and finally, with respect to mixed derivative with respect to mu and sigma, excuse me, the mixed derivative will be minus 2 over sigma cube times the sum of the log of xi minus n mu, right? So these are the three second order partial derivatives. Now we need to work them out at the, we need to work the values of these partial derivatives at their estimates. So starting with the first one, which is this, at mu equal to mu hat and sigma equal to sigma hat. All right, you will get, excuse me, this will be equal to minus n over sigma squared hat. All right, and for the second one, I'm not going to do the simplification. I mean, I'm sure you know how to simplify, how to do the, how to compute this. I mean, I'm not, so it's going to be, I mean, you should do the math. I'm sure you're better than me. I mean, you should do the math for the second one, right? This is what you will, this is what you will get. You get minus 2n over sigma squared hat. This is what you will get. I'm sure you can check it, right? All right, that's what you will get. You should substitute mu by mu hat and sigma by sigma hat, and simplify things. You will get this, right? And finally, the mixed derivative. And you should do the same thing again. That replace mu by mu hat and sigma by sigma hat. This will become a 0, right? So okay, now we can check the conditions. So the conditions that we need to check are, okay, the first condition is that the first condition is this, right? That this guy here must be positive, right? Which is, sorry, negative, which is clearly the case, right? So the first condition is clearly satisfied. And the second condition, excuse me, the second condition is that this is the second condition, right? And if you do the math, I'm sure you guys know how to do it. If you do the math for this, you will get 2n squared divided by sigma power 4 hat, which is clearly positive. So hence, the two conditions that the two conditions are satisfied, right? So the conclusion is this, right? So the hence the this and this, right, are MLEs of mu sigma squared. Is that clear, guys? I mean, this is very similar to the previous example, except you are dealing with the log normal distribution, which is slightly different from the normal distribution, right? You guys okay with this example or not? Any questions you have? Hello, guys. Are you okay with this example? Yeah. So I just done two examples on how to find MLEs when you have a distribution that has two parameters. So like the normal distribution or the log normal or the beta or the Gumpel or the Laplace. There are so many distributions, I mean, in statistics that have two parameters. So you can apply this procedure to find the MLEs of distributions with two parameters, right? And I'm sure you will learn this in statistical methods next year two. And I mean, you will learn more than what I just taught you, but what I just taught you is just a simple thing, right? But I hope it will help you with the course you will take next year, semester 2. All right, guys. So this is the last lesson for intro to stats. But I will, you can still I will not be teaching you in year 2, but as I said, I only teach year 1 and year 3. But you can still contact me like every day, 24/7, for any questions you guys have about the material I covered, or about anything. I mean, about some future course that you plan to take. All right, just any questions you guys have, just feel free to contact me 24/7. All right, guys. So, but otherwise, I hope everything is well with you guys, and take care. I'll probably see you in September when you guys come back. Hopefully, the uni will be open in September, so that I can see you guys in person one more time. So I hope you guys take care of yourself in the meantime, and and stay safe wherever you are. Yeah. Okay, guys. So I wish you well, and once again, any help you need, feel free to contact me by email or by Zoom. I keep Zoom 24/7, as you know, so you can contact me anytime, any day. Okay, so I will talk to you later. So just take care of yourself, right? Okay, guys. Bye, guys. Bye.
Thank you, sir. Thank you for teaching this semester.
Yeah, it's really my pleasure teaching you guys, and I hope I did my best to teach you guys every week using.
I'm glad to be your student. Thank you so much, sir.
Thank you.
And I wish I will see you in September, and take care of yourself.
Yeah, you too, man. You too. You take care of yourself too. I'll probably see you in September. Yeah, and you
Yeah.
come back, and you come back to Manchester. Yeah.
Okay. Thank you, sir. Bye.
Bye. Bye.